Subspace is a vector space with operations addition and scalar multiplication defined over it. These operations contain an identity element. They also contain, they also hold true for associativity and commutativity. And addition in particular also requires an inverse element. The vector space V in this diagram here contains the subspace, which is also a vector space, U, which also contains the zero element. We note that the zero element is contained in both vector spaces as it's necessary for an additive identity element.
So in this example, we say that R2 is a subspace of R3. R3 is defined as three-dimensional, basically, and R2 is a plane falling within this three-dimensional space. Any plane, really, which includes the zero element, indicated here with the red circle at the origin, and also following scalar multiplication and addition. Over to the right-hand side, we have vectors A and B defined, such that A plus B also falls within the plane of R2, and 2A plus 2B, being scalar multiples of A and B, are within the plane as well. Any plane can be defined within R3, and if it includes the origin, will also be a subspace of R3.
For another example, we look at music. A vector space of all sounds can be defined, and then if we consider the notes on a piano keyboard, we can say that this is a subset of sounds. We want to determine whether or not it's a subspace. For this, we are going to use the notes that we just heard as elements in our vector space. We're going to claim that scalar multiplication takes C, and a 2C is one octave higher. The addition element, for addition, we define the zero element to be silence. We define a note plus silence to be the same note, as we can hear. And we define a note plus another note to be a chord. Associativity and commutativity hold in this case. However, if we try and take a note and add some other note to it, it doesn't really matter what we add, we can't find a negative note. So there is no additive inverse, and not a subspace.